In this example, we're going to look at an application of Hooke's law. Hooke's law tells you that imagine you have a spring, okay? And you are not touching it. So it's in what we call equilibrium, right? This is called natural length of a spring. So if you just leave it alone, it's going to have a certain length, okay? So usually we'll denote this by L sub 0. So L0 is our natural length. And in this case, it's 22 centimeters. Now, you immediately need to convert this to meters, okay? And the way you would do that is divide by 100. And that's just going to give you 0.22 meters. So, because the metric system, you need everything in meters. Okay. And so that's the natural length. Then imagine that you are stretching it in addition to whatever it was natural length. You're applying some force. And now the new length, so let's just call it L1, is 26.5. Okay, it looks like it's 26.5 centimeters. So the Hooke's law says that the force that's required to stretch it by a certain amount is proportionate to that amount. And K is that constant, is sometimes they call it spring constant or something like that. Okay, so what do we have here? We know that the force, so we know F, force, is 0.09 Newton. So we need to figure out, okay, what is that spring constant? But what happened is we applied this force and it stretched from 22 centimeters to 26.5, which is 0.265 meters. And what we need to know is figure out this x, by how much was it stretched. And you're not taking this new length. You are taking the difference, because this x is the difference between the natural length and the new length. So if I take 0.265 and subtract 0.22, I will get 0.045, okay? So from here, I can solve this for k. We're going to have 0.09 multiplied equal to k multiplied by 0.045. So let's just divide. Let's use the calculator. So if I take 0.09 and divide it by 0.045, that tells me that k is 2. Okay, so that's my spring constant. The next thing it says, okay, how about, again, you let it go, it comes back to its whatever equilibrium, which is natural length, and then you want to stretch it to a new length of 29 centimeters, okay? So you are stretching it again, starting at the natural length, which is equal to 0.22, and you are now stretching it to a new length, let's call it L2, which is 29 centimeters or 0.29. Okay, so let's set up an integral to find the work that's required. Now, work, you should know that, that's an integral of force. And the limits of integration would be what? Well, that's how x changes. Well, in the beginning, your x is 0. Why? Because the spring is it's in equilibrium, right? Because that's from natural length. So at first, your stretch is 0. You're not doing anything. The new one, though, is stretched from 22 to 29. So that's 7 centimeters or 0.07 meters. So this should be 0.07. So you are subtracting these two. Okay, so this is not going to be 0.22 to 0.29. That's a very common mistake. Instead, you are looking at the difference between the natural length and a certain length. So in the beginning, it's 0, and then it's 0.07, okay? And we're integrating the force, but according to the Hooke's law, the force is k multiplied by x. Okay, so this is going to be kx dx. All right, so let me go ahead and start filling this out. So this is 0 to 0.07. Now my k is 2, so I'm going to have 2x dx. Okay, now this integral is super easy, and these problems generally are easy as long as you remember to convert everything to the correct units. That's like what trips most people up. So if I have just 2x, the integral is x squared, and then I substitute 0 and 0.07. Okay, so at 0, obviously, this is going to be 0. If I take 0.07 and square that, that's going to be 0.0049.